And so you can't see it here, but that's where the magnet is. It's sitting behind it. And it causes, instead of the stream dropping like you would expect from your faucet, it slings it around.
Whoa. So what is that? There's like metal or something? What is this stuff?
Yeah. So it's kind of the heart of it is gallium. And, gallium is just an element that's on the periodic table. And what makes gallium really special is that it's got a low melting point. So if you were to hold it in your hand, it would melt. Actually, I should have brought more props, but I have a little bit of it here.
Is it toxic?
No. So that's kind of the other funny thing. So usually when I tell people I work with liquid metals, they think of one or two things. They either think of mercury, which is toxic, or they think of the Terminator, which is, scary bad guy. And so, no. So I always have to be a little bit careful because I don't think that gallium has been super carefully studied, but but sort of one way to think about it, or what I tell people, is that the melting point of a material doesn't correlate with its toxicity, right? So if you think about water melts at 0 degrees Celsius, but that's obviously it's not toxic. So the only reason people think mercury, like metals, would be toxic is because of mercury, which is toxic. That said, gallium is not found in our diet, so it's not something that you would have naturally in your body. So usually tell people to be a little bit careful, but the body, if it does get inside your body sort of treats it like it's iron. So if you take like my wife sometimes takes an iron supplement to keep from getting anemic, and that ultimately kind of makes its way through your body, and gallium does the same thing. So there's that. And then the other kind of weird thing about it is it has no vapor pressure. So what that means is, if you take a shower and you dry off with a towel, you hang up the towel, the water will evaporate. You come back the next day and the towel is dry. But this does not evaporate, at least not at room temperature. And so that's important when you ask about the toxicity, because it means you're not going to worry about breathing it. So you see, I've got this right here in the office. I would open it, but.
And if you ate it, it would just be like iron?
Well, I probably wouldn't eat it. I've gotten it on my skin before, not on purpose, but yeah, it is considered to have low toxicity. So we had a collaborator who came to me a few years ago. Was a really brilliant guy, but he had this idea of using liquid metal for drug delivery. And I looked at him the same way you just looked at me, like, interesting, but kind of a weird idea. And it turned out to work. And as part of that study, when I say we, it was a collaborative effort, but we made little particles and put them into mice, and the mice were able to kind of figure out where it goes. And also, just kind of a funny story. I had a doctor contact me. Gosh, it was probably about a decade ago. And they were interested in using liquid metal for wires for pacemakers. So I would literally be inside the body. Now it would be encapsulated in rubber or something like that. But the idea is that if you have a pacemaker, there's a battery source, and then there's the pacemaker that's sending the signal to tell your heart to beat. And that wire looks like kind of like a spring. And 99.9% of the time it works great. But if it breaks, that's bad news, because that means your heart's not getting the pacemaker signal. So he had the idea of using liquid metal as a wire to sort of be indestructible, so it could stretch, and that's one of the things that's really cool about it. But anyway, one of the concerns was whether it was going to be toxic, and so he said they were going to do some experiments, and I told him, "Oh, that's great! I'd really love to see the results of those." And he said, "Okay," and I didn't make much of it. Well, about a month later, I got a package in the mail, like a FedEx envelope, and I took it out, and it looked like shrink wrapped chicken, kind of like flesh or something. And I was like, what is this? And so I contacted the doctor and said, I got this package. I can't make any sense of it. What is that? And he said, oh, that's the rabbit. And I was like, when I said I want to see the results, I was thinking of a plot or a graph or just a write-up, but I didn't actually need to see the so anyway, this is a long answer to a short question, but they had injected it into rabbits as part of a controlled study. And, the rabbit was fine, other than the fact they had to dissect the rabbit to figure out make sure everything was okay. So anyway, I'm still not at the point where I would swallow it on purpose, but I also don't panic if I get it on my skin, or even if I got a little bit in my mouth. I'd probably, I wouldn't be happy about it, but I wouldn't panic.
That must be an interesting colleague you have, or I didn't know if you said colleague or friend, but to ship you the rabbit. Yeah.
Yeah. It was not the whole rabbit. It was like what you'd see if you bought chicken at the grocery store or something.
Yeah. Well, he did the work for you, right? He cleaned it for you.
Yeah. So
did you ultimately get the data on it?
It wasn't like a full-fledged study as far as I know, but they injected in the rabbit. Of course, when you inject anything into your skin, you're going to get a little bit of irritation. So I think there was some irritation, but it didn't cause the rabbit to die. It didn't cause any, I don't know. I'm not a doctor, but it didn't cause anything to cause concern. And actually, gallium has been FDA approved. So that's kind of the ultimate thing, but it's been FDA approved for different pharmaceutical applications. And it was FDA approved as a MRI contrast agent. So like when you go get an MRI done, but it turns out there's ones that work better, so we don't use it. For a while, it was explored as a replacement for mercury. Actually, I just went to the dentist yesterday and got a filling. Now they don't use metal anymore, but when we were kids, they use metal amalgams, and those use mercury. So they looked at gallium as a replacement. So there's kind of been a bunch of here and there studies where people have looked at it, but all of these things that I'm mentioning to you it's kind of a subtlety, but what I'm showing you here is gallium metal. But if you take a vitamin that has iron or magnesium or any of these kind of micronutrients that you hear about, those are metal salts, right? Just like if you put table salt on your French fries, sodium is a metal, but when you're eating it on your French fries, you're eating sodium salt. And so those metals don't have really a way to dissolve into your body. It's the salts that are ultimately being used for a lot of these applications. But for that one study I mentioned, we did put actual little blobs of liquid metal in the body, and that was also fine. But again, for your listeners, I wouldn't recommend eating it.
And is it being used in any commercial application today?
So there are, and it's kind of funny the timing of this talk. Earlier today, I was just hosting a group of 8 or so people that flew down that work at a company that makes some of these materials, and they use them for a number of different applications, and they're here just visiting. But probably the most high profile one that just came out recently was in the Sony PlayStation. They are using liquid metals to help dissipate heat from the computer chip that goes inside of the PlayStation. So there's videos you can find online. They call them delidding videos, where they take apart the PlayStation. And sure enough, there are liquid metals in there. And the idea is that as transistors get smaller and smaller, and you pack more of them onto a chip, it generates a lot of heat. And metals are a really good way to remove that heat. That's not the most exciting example, but the point is that there are examples where people probably have this in their house and they probably don't even realize it because it's inside the packaging. Gallium itself is used for some other things. It's used as a precursor for some semiconductor materials called gallium nitride, gallium arsenide. These are like high performing semiconductors. So there's that. People use them at research universities for a very sophisticated tool that's called a focused ion beam. Have you ever heard of that?
No.
So it's called FIB. It's a beam inside of a vacuum chamber. It's a beam of ions that they literally focus down, kind of like a laser beam, but with ions, and they can use it to cut materials. So it's pretty wild. So those are like things that are in existence now that use this particular material. But what we're trying to do, and other people, we're trying to use it kind of for more futuristic things. So,
like what?
Yeah, like what? So one of them is trying to make electronics that are soft and or stretchable. So, most electronic devices that you encounter in your day-to-day life, like the computer that we're talking on now, your cell phone, all these things are made out of rigid materials, but our bodies do all these amazing things and they're essentially soft. If you take away the bones, you're like, the stuff that does most of the work, like your brain, your fingers, your muscles, all this are made out of soft materials. So part of this is sort of a little science fiction-y, can we use that as inspiration? But I think there's also some practical things, like people are looking at wearable devices or making electronics into clothing that could actually deform, be worn comfortably on the body. There's also this entire little subfield that's called soft robotics, and I'm kind of on the periphery of it. But the idea is to try to make, when I think of a robot, I think of something that you might see in like a car factory with like sparks shooting and these like robotic arms moving around. Not a very safe place for humans, but there's this idea of trying to make robots soft, more like an octopus, because you have sort of unlimited degrees of freedom of motion. An octopus can fit through like a beer bottle, can contort itself. It can wrap around and grab things. It can do all these complex things, but it's completely soft. And so, if you can start imagining putting sensors or other electronics inside of a material that's like that, that's also kind of, of interest. So those are some of the things. We can go there. There's actually part of the group of people that are here today. They're interested in 3D printing. So, there's these 3D printers that can print plastics, print polymers, but they're not compatible with printing metals. So one of the videos I can show you later, we take 3D printed parts and then we inject liquid metal. So it allows you to pattern the metals in ways that just aren't possible with copper or aluminum, because it's a liquid at room temperature. And I haven't even said this yet, but probably like the most important thing for us, and the reason a lot of this works, is that the metal reacts with air on its surface and it forms a skin on its surface. Actually, you'll appreciate this. It's just right over here. I'll grab it.
Yeah. Okay.
So I'll start with this one. So this is just gallium, and my student molded it into the shape of North Carolina. And I'm holding it like this because if I held it, like this for too long, it would melt and turn into a puddle. And the viscosity of this metal is, when it melts, it's like water. So think of it like a metallic water in terms of the way it flows. And so this is a droplet of it. Actually, this is gallium and indium. So we've added another metal to depress the melting point. So I know it doesn't snow very much in Nashville where you live, and doesn't snow very much here either. But when it does, they put salt on the road, and that lowers the melting point of the water, right, to keep it from freezing. You can do the same thing with metals. So this is, and people have known this for a long time, but this is gallium and indium. And so it actually is truly a liquid at room temperature. I don't have to use my body heat to melt it. But you'll see, if you've ever seen the movie Terminator, you'll see that this is kind of like what you would expect with mercury. It's like a ball of metal. And another interesting thing about this material, it's got the largest surface tension. So remember, it doesn't evaporate. That's very, very weird. It's got the largest surface tension of any liquid. So to demonstrate that to you, if you take salad dressing, like oil and water, and you shake it, it forms a bunch of little droplets. Well, this one, if I shake it as violently as I can, it did form a couple droplets, but it very quickly goes back together. So the surface tension of water is, I'm not going to tell you the units because it's not important, but it's about 70. This is like 700, right?
Wow.
So it'd be like walking around on Earth and seeing a bunch of people that are like 5 feet tall, 6 feet tall, 5 feet tall, 6 feet tall. And then all of a sudden someone that's 50, right? Yeah. Like it's
like Dwayne thing. Johnson.
Yes. Yeah. He is like King the Rock. So that's very unusual. It's not like shades of gray. It's like most liquids you encounter day to day are down here, and this one's like way up. But anyway, so that if to get to my point, this is another vial of that metal, and I don't know if you can see, but there's like a little window through it. The first one I showed you has a clear liquid. Maybe you can see it, and that clear liquid is a base. It's got a high pH, and that base is important because it keeps the metal free of oxide. It keeps when air reacts with the metal, it forms an oxide, and this will dissolve it away. So it acts like mercury. But this one, which doesn't have it, it's just in air. It's got this oxide layer, and that oxide layer is like a shell that forms on the surface. And you'll see later when we show you the videos, we can use that to actually shape the liquid. So in this one, when there's no shell, no matter what I can bang on it and whatever, but it ultimately forms a sphere because of the surface tension, the Dwayne Johnson surface tension. And this other one, which is exactly the same material, but because it's reacted with air, it forms a shell on its surface. So, think about what happens to a waterbed. If you remove the shell of the waterbed, the liquid just flows out. But this one's got the shell that holds it in
How
that shape.
tough is that shell? Is it like normal metal?
So that shell is an oxide, so it's actually a glass. So it's not very strong, and it's only 3 nanometers thick. So it's only a few molecules thick, tens of molecules thick. So it's very thin. So if you were to touch that, it would feel like wet paint.
Okay.
But that's important. We actually want that because when we put this into a stretchable wire, like I've got one here, this is just a piece of rubber and the metal is inside of it. We've actually injected it inside. That's why it looks like kind of like a barbell shape. We had some holes, we injected it. And this is a slightly more sophisticated one. It's kind of hard to see. Let me see if you can see it. Yeah, there we go.
Oh, so that's very cool. That looks like a circuit or something.
Yeah, so this one's like an inductor. So this is like what's
like traces.
Yeah, it's just traces of metal. So you can pattern it in ways. And this just to kind of emphasize my point, it's the same metal that really, really wants to beat up. And the difference is that when you do it in air, because of the oxide that forms on the surface, which again is very, very thin. That allows it to hold its shape. And so we can actually 3D print it. We can print it into shapes, like you can stack droplets. You can.
But if you touch it, how come it doesn't just like mess up? Like how's it retaining its shape against the pressure of your hand holding it?
So in this particular example I'm showing you, we've got it encased in rubber. And so that kind of helps it hold its shape. Just like, with a regular wire, like you have the wires to charge your computer, you've got typically copper inside, and then you've got some polymer on the outside. But in this case, the metal conductor is a liquid. So that's also interesting because like I see on your microphone, you've got like some wires coming out of it. If you made those wires out of rubber and then the metal part is liquid inside of there, you can make wires that can stretch as far as the rubber will allow. So we've made headphone wires that are, and there's some videos we can look at, made headphone wires that can stretch, 10 times the original length. So it kind of gives you the best of both worlds. You get the conductivity of a metal and the stretchability of a rubber.
How did you get introduced to all of this?
I was very, very lucky. So actually my PhD, believe it or not, was on a different topic. I was studying polymers, which has come in handy, but I've kind of gone off the reservation a little bit here. So I didn't even know what liquid metals were when I was a PhD student, but one of my friends, good friends during my postdoc is like a kind of an apprenticeship that you do between once you get your PhD and then before you become a professor. So I met somebody then, and still a good friend to this date. And he had made the observation that if you took these liquids and you touched a drop to a surface and then you pulled, it acted more like bubble gum. In other words, it formed like a cone shape. They call that necking, where the liquid will kind of pinch in. Whereas if you do that with a droplet of water and you touch a droplet of water, I mean, heck, I can do it right now. I've got my water here. If I touch a droplet to my hand and then pull away, I just end up with 2 puddles, one puddle on the tip of my finger and one on my skin.
Right.
And so he made this observation that it formed kind of more like what bubblegum would do. And so that raised the question, like, why is it behaving this way? And well, the answer ends up being pretty simple. It's reacting with air and it's forming a solid shell on its surface. And oh, by the way, I didn't mention this, but that shell forms so fast that it's basically immediate. So one time on accident, we accidentally squirted some of the metal out of a syringe, like out of a nozzle, and it came out and it formed a fiber, like it formed a wire. So, like when you turn on your garden hose, it forms a cylinder of liquid, but that cylinder eventually breaks up into little droplets because of surface tension. This is like shooting a liquid out of a hose and having more hose form around the liquid. It's like forming its own shell as it goes.
Oh, because the syringe or the nozzle was metal.
Well, the syringe was metal, but when you shoot it out, it starts reacting with air, and the air reacts, it forms this shell as you go.
Yeah.
So you can sort of form its own container in a way.
Have you looked at it performing that action under like a high-speed camera?
We have done some. We do have a high-speed camera in our lab, and those are super fun to play with because you can see. I think a normal video plays at like 30 frames per second, like probably what we're seeing on the computer. But these can do, tens to hundreds of thousands. I think the state-of-the-art cameras can do 1 million frames per second. It's just incredible. And we have looked at that, but just not that particular process. What we have done is we've looked at what happens when you bring two of these droplets together. The question is like, do they sit on each other, kind of like building a snowman where you just stack liquids, or do they merge together and form a bigger droplet? And the answer is it sort of does a little bit of both. It merges together, but then it stops. So you end up with kind of looks like a figure eight, where it's they merge together, but but not into a single drop. So we've used that actually to our benefit to make self-healing circuits.
Wait, so they penetrate each other's shells, but they don't fully merge.
Yeah, so I believe it's really hard to study because you can't see inside. You can't see what's happened when you touch the material together because it's a metal, it's shiny. So you can't see it optically. A lot of like what we call like spectroscopic techniques don't really work. So we kind of infer it based on the way it flows. And also what happens when you pull them back apart. So if you touch two droplets very gently, you can pull them back apart. But anything other than that, they actually will merge back together. And I think what's happening is that very thin shell is breaking. So again, it's not a perfect analogy, but it's sort of like touching two water beds and then the water connecting between the beds. Now, the question is what happens to that shell of the water bed, and what I think is happening is it's just breaking and you're able to make metal contact. So we've actually used this, and there's another cool video we can see, but where you can take a wire of this stuff and cut it. And when you cut your skin, sometimes blood comes out, but usually it forms a scab.
Hopefully.
I don't know what else could come out, but when the blood does start coming out, it forms a scab. And actually part of that is triggered. There's a cascade mechanism whereby that happens, but it's triggered by oxygen. And this is sort of the same thing. When you cut it, the metal gets exposed to more oxygen and forms a new skin. And so it doesn't leak out. So like this thing that I showed you, the little sophisticated circuit, if you were to cut this with scissors, the liquid doesn't come out. It stays flush with where you cut it. So then this is actually sort of boring. It's just silicone, kind of like bathroom caulk, like real common. Maybe we get to see the video.
Yeah, but if you try to pull up some of the videos.
Yeah. So this was an example of just kind of a fortuitous discovery, but we've found that if you apply a voltage to this metal, it will lower the surface tension significantly. And just by good timing, this came out around the time that the new release of Terminator came out, so it got a lot of interest. It even got picked up by Seth Meyers. I don't know if you know the comedian.
Yeah.
He made fun of our research on late night TV.
Dude, you've made it.
I know. That was the highlight of my career. Really was exciting. But anyway, what's happening here is literally like that vial that I showed you with the bead of the liquid metal. We're taking that exact same scenario where it's like wants to be a ball, and just by applying 1 volt to it, we cause now this has to be done in water, but when we apply 1 volt to it, that causes, they're called electrochemical reactions, or just reactions that happen due to the voltage. That causes the surface tension of the liquid to become low, so low that you can actually pump the liquid out without, like you're seeing here, forming a cylinder. So there's a phenomenon that everybody has experienced that's called a Rayleigh instability. named after Lord Rayleigh. It's discovered or named in the late 1800s. It's been known for many, many years. And it's just known if you take a fluid and you pump it out of a nozzle, so go home, turn on your faucet, you'll have water coming out of the faucet, and it will look like a cylinder. But that cylinder is not stable because it will eventually break up into droplets. And that's due to surface tension. But in our case, we can apply the voltage and lower the surface tension so much it will just come out and never form droplets. It will form a cylinder. So you remember the Dwayne Johnson surface tension thing?
Yeah.
We're taking Dwayne Johnson and turning him into like a feather, like nothing. And we're doing it with 1 volt, and it's completely reversible. So when we turn the voltage off, it goes back to being Dwayne Johnson. It goes back to being 700. And when we apply the voltage, it goes down to close to 0. So that's wild. And it's hard for people. I can
see why you're so interested in this stuff, and you're spending time. I get to talk to scientists, here and there, or researchers and professors, and I can almost like always see like the full extent of it, in the conversation. I'm like, oh, okay, cool. I kind of wrap my mind around this. This seems like there's still stuff to discover about this material.
Yeah, so sometimes I describe this material as like solutions looking for problems, because it's got so many unique properties that sometimes people, they have the same reaction you did. Oh, liquid metal must be toxic. Oh, liquid metal, it must be mercury or something. And so I don't know. Feel kind of funny saying this because, like I said, I didn't even know what it was when I was a grad student, but I'm kind of going around telling people how cool this material is. And we haven't even, we barely talked about the electrochemistry stuff that's really interesting. It also can do some really interesting things, like for electrochemically. It's called catalytically. So it can help drive certain reactions, including reducing carbon dioxide. So there's some really nice work done in Australia, some of my friends in Australia, where they've shown that you can convert CO2 back into carbon. Now, that sounds like a miracle material. And of course, there's more to the story. You got to have some energy source to do this. But the point is it does things that just you wouldn't necessarily think of. If you want to, while we're on the topic, since we just saw that previous one, okay, to me, this one is like mind blowing. If you can go to the one that says liquid metal magic. Okay, so here we go. So here we're pumping liquid out of a nozzle, and like I said, it's going to form droplets. That's exactly what you expect from 100 years of physics. But when you apply this voltage, it forms a wire. That's crazy, because the only way that thing forms is if the surface tension is very, very low. But this is why I wanted you to see this particular video. Pretty much everybody in freshman physics learns this. Sometimes they call it the right-hand rule or the left-hand rule, but basically if you have a wire with a current going through it and you bring a magnet close to it, it generates a force. And that's called the Lorentz force. In this case, because it's a liquid, it's really soft. That force, which you'll see in this little depiction, you got your magnetic field, your current at 90 degrees, and then the force coming out of plane, out of that plane, that causes the metal to move. And so you can't see it here, but that's where the magnet is. It's sitting behind it. And it causes, instead of the stream dropping like you would expect from your faucet, it slings it around.
Whoa.
Yes. And then when it gets to the edge of the magnet, it experiences what's called Lenz's law, which you've probably also learned about at some point, and that causes it to slow down. So if your magnet is a square, you can sling this metal into the shape of a square. And this is the size of a human hair. So it's the Dwayne Johnson of liquids. We're making it into a cylinder. So you're squeezing Dwayne into a cylinder. It doesn't want to be, Dwayne Johnson wants to be the sphere. And, but not only that, we're slinging it around. And by the way, gravity is down. So this is suspended in solution, just like hanging out. Now, what is that good for? I don't know. Maybe you can tell me, but it's just jaw dropping. And this is work that was led by, a group also in Australia, and I was able to contribute. You can see the names there, Professor Wong. But anyway, just crazy.
So one of the breakthroughs here, as far as science goes, is that this is a novel non-contact method to manipulate and shape fluids. Are there other fluids that can be shaped without contact? That can also act as like a metal?
No. It's very difficult. So usually when we want to manipulate fluids, we put them into pipes. Like if we want to flow water to our house or something, we put it in a pipe and flow it underground. There's tricks to manipulate droplets, like to suspend droplets and kind of get them to levitate and stuff like that. But as far as I know, there's nothing that could first of all, take a stream and make it into a cylinder, and then also just get it to move at will. So I don't know. There could be some kind of cool stuff that maybe could be done here, particularly with like patterning the metal and using it somehow for circuits. But so I'd mentioned that this wire that you were looking at is just silicone. It's really boring, not fancy at all. So this is what I'm telling you. It's like when you cut your skin, the blood gets exposed to air and it forms a scab.
Yes.
Here, the metal is getting exposed to air, and the scab is that very thin oxide. Well, that keeps the metal. So you can see this is like a slab of, or basically rubbery material. It's that brown stuff, and then the inside of it is a liquid metal wire, and there's electricity going through it that's lighting up that LED. And when you cut it, that of course breaks it mechanically, but it also breaks it electrically, so the light turns off. Now, the key idea is that the liquid doesn't come gushing out. It just like a scab, it stays flush with that interface. And when you bring those two pieces of the circuit back together, it will heal electrically. So the light turns back on. And then the polymer is a special polymer. It's held together by hydrogen bonds, which generally are weak relative to covalent bonds, which hold most of our world together. But there's enough of them that the material is a solid. And so you don't do anything. You just wait a few minutes and it's now gone back together. So it's healing mechanically and electrically.
Whereas if you did that with another type of metal wire, it wouldn't actually bond back to itself. It would just be touching the other one.
So now you can imagine why we were studying what happens when you bring two droplets together. If they didn't merge together, it'd be kind of a bummer, but they do merge together. So when you try to pull those things back apart, it's actually, formed a wire.
That's cool.
And we're not the only ones. I mean, we did that work that I showed you, but there's other people working on self-healing materials, self-healing circuits that, you could in principle scratch with a razor blade and they'll sort of go back together. And none of them work as good as the body. I mean, the body really not only heals, but it kind of repairs itself. But
dude, this is awesome. This is way cooler than I thought it would be. like it was cool, but you're a really good teacher, man. You're really good at communicating and explaining things, and you're pleasant to talk to. So your students are very lucky, because I remember going through school and it was rare that I would get a teacher that was great like you.
Oh, thank you. Well, there's not a lot of things I do well, but I do like sharing our work and teaching it. But I don't know. I'd probably flip that on its head a little bit and say that I'm lucky to work with the students. We have really good students here, and everything I've shown you was really done by students. So yeah, it kind of cuts both ways. But thank you for saying that.
Yeah, if we've got parents that we got a lot of parents that listen, and they might want to direct their kids at some of this liquid metal type stuff. Tell me a little bit about what you would suggest to them as far as this being something in the future that they might want to start early learning about.
Yeah. So, well, they're at the right place if they're listening to this podcast. Do have a YouTube channel where, if it's a young kid, I think a lot of times I wonder about the impact of our work. We're scientists, we publish papers, and kind of sometimes I like to joke, I'm happy if 20 people read one of our research papers. And of course, it's more than that, but it's on that scale, tens to hundreds of people. But these YouTube videos, it really helps make a lot of this accessible. So a lot of the work that we do is essentially funded by taxpayer dollars in many cases. And so I liked putting it out there and kind of giving back and hopefully getting people excited about it. So that'd probably be the first place I'd start. I've got a TEDx talk that's I think does an okay job at sort of explaining why the material is interesting. But then, beyond that, believe it or not, you can buy gallium on Amazon. Again, don't want to You don't want to eat it. If you do eat a little bit, it's not going to hurt you. But this is not super exotic material. So actually, gallium is right below aluminum in the periodic table. I didn't mention this earlier, and you might remember from like high school chemistry that if they're in the same column, that means they're like brothers or sisters. They've got very similar properties. But the big difference is gallium melts at a very low temperature. And oh, by the way, gallium melts at 30 Celsius and it boils at over 2000. It's like 2,400 or something like that.
I don't know a lot about this stuff. Could it turn into a gas?
So if you heated it up enough, you would start evaporating it. But I think people in the literature, the lowest temperature where I've seen somebody even be able to measure what we call vapor pressure is 500 degrees Celsius. So that's way hotter than your oven could go at home.
Yeah.
So yeah, in practice, if you're just playing with this stuff, it'd be difficult. Now you can react it with other things, and when you react it, you can form gas. Just like if you cook on a charcoal grill, you turn a piece of charcoal into carbon dioxide and it becomes a gas. So you could do something like that. People call those like metal organic precursors and stuff like that. So you can make gases that contain gallium, but if you just bought the metal, it would not be. But anyway, that's another place. There are, I think it used to be, at least like if you go to Walgreens or drugstore kind of place, some old-fashioned thermometers. I don't know why anybody would buy the old-fashioned thermometers when you can just buy kind of a digital one. But anyway, I have one of these here, and it's got gallium. I think This is actually gallium, indium, and tin. And again, those are like adding salt to lower the melting point. So that's another commercial product. It's not super high tech or anything, and we're trying to think a little bit beyond that. So those are places where you could, if you really wanted to get your hands on some of this stuff. I will mention another. It's kind of good it's an interesting thing, but it's kind of a bad thing about this. There's two things. One is that gallium is expensive. So a gram of this stuff is about $1 or less than $1, which, depending on what you compare it to, could be cheap or expensive. But so I can't imagine a world where we're going to be making like power lines with this material. But like the little thingy that I showed you here, this is actually an antenna. This is like a few pennies worth of material. So in that sense, it's not cost prohibitive. So, but anyway, that's kind of one downside of this material. And then the other, I'd call it a feature. It could be good or bad, but it will form metal bonds with other metals, and in some cases can do so very aggressively. So in the case of aluminum, it will diffuse into what's called the grain boundaries. So the boundaries between aluminum crystals. So if you have a piece of aluminum, like aluminum foil, it's a bunch of crystals that are all connected together, and it will go into the boundaries between those, and it will cause it to fall apart. So that's called embrittlement. And that's bad news if you have something valuable made out of aluminum, because you could literally take a piece of aluminum foil and it'll just crumble apart when aluminum or gallium.
Then that's what we should make all the Android robots out of.
Exactly. That's how we'll take them down.
Yeah. Gallium guns. We're doing it. Got super soakers full of gallium. Yeah.
I love it. Yeah. Yeah. And you could actually make, because of the thing I was telling you earlier, you could squirt it out and it would look like a laser beam.
Yeah. That's what we could do.
Yeah. It doesn't do it with all metals. Like we found stainless steel and copper, it doesn't do those things. But anyway, it's one of the concerns people have. It's like, well, if I put gallium in my fancy computer, like, is it going to destroy the computer chip and that kind of thing?
Is there anything that does that to plastic?
Yes, and from a different mechanism, but not nearly as kind of cool. So there's what people call plasticizers, which are actually these days kind of a no-no, because plasticizers are sometimes used in plastics and they can end up in drinking water and that kind of thing. But plasticizers are just like molecules that can go in between the polymer chains and help them kind of expand and become softer. So there's a great example of this is, PVC pipe that you probably have in your house, right? It's like really hard, rigid material. That's PVC, polyvinyl chloride. PVC can also be used for shower curtains, which are nice and soft and pliable. And the difference is the shower curtains have plasticizers in them.
Okay.
And actually, the new car smell, I was told, I never actually looked this up, but I was told that those are also plasticizers that are in the plastics inside the car. So it smells nice, but you're not really supposed to be breathing them.
That sounds about right for humans, right?
Yeah. But anyway, it's not as dramatic. The aluminum, it like just crumbles apart, you know.
So we should write Elon Musk on Twitter and say, hey, when you're making your army of humanoid robots, make them out of aluminum, please. Thank you.
Great idea.
Well, dude, Michael, man, we made a podcast. How do you feel?
Oh, it's good. It's my first time on a podcast. And
oh, really?
Yeah.
Oh, nice.
Yeah. I've been invited before, but I didn't know how serious the invitations were. And I appreciate that you guys did your homework and made me feel real welcome. So thank you.